Hello, everyone. My name is Fu Bin. It's my pleasure to introduce our recent work, Neural Transformation Fields for Arbitrary-Styled Font Generation, in CVPR conference. In this work, we focus on few-shot font generation task, which generates arbitrary-styled font images with a few samples. Recent style content disentanglement approaches mainly focus on exploring powerful style representations, which ignore the spatial transformations in transferring font styles. In this paper, we propose the novel solution and model to solve above problem. We model font generation as a continuous transformation process, from the source character image to the target font image, by the creation and dissipation of font pixels. To model this transformation process, we construct a neural transformation field to embed the corresponding transformations quantities. Now, let's talk about our font generation model in details. As shown in Figure 2, the differences of font styles mainly come from the shape deformation and transformation of the source font, such as the thickness of strokes and the writing pattern of glyphs. Based on this observation, we regard font generation as a continuous transformation process from the source font to target font by the creation and dissipation of font pixels. The creation intensity phi represents the non-font pixel changing to font pixel, or the font pixel enhancing its intensity. The dissipation rate tau represents a font pixel weakening its intensity with the rate tau. To model this transformation process, we construct a neural transformation field to embed above transformations quantities. Figure 3 provides the methodology of our model. In the neural transformation field, the origin point stands for the standard font style, and each font style is represented by a specific location theta. We employ a style estimator E theta to predict locations of each font style. With these definitions, the font generation process can be viewed as the transformation process of font pixels from the original point to the target location. Considering the arbitrary character generation and the fine-grained structure variations in font style, we further generalize our NTF in Figure 4 by introducing the structure embedding and localized style locations. Once we obtain the creation intensity and dissipation rate along the transformation path, we can collect these intermediate transformation results and formulate the font generation as a font rendering process in neural transformation field. Now, let's discuss the font rendering process for font generation. The transformed intensity at the location omega can be expressed as the following differential equation. In this equation, the first term models the creation process, and the second term models the dissipation process of font pixels. The solutions to this differential equation are shown in equation 2. This equation is the font rendering formula in our NTF, and the quantity T omega represents the accumulated transformations along the path from the location omega to theta. In practice, we estimate this continuous integral numerically. The interval from the original point to the target location theta is partitioned into n evenly spaced segments, and we draw one sample in each segment. Based on this sampling method, the font rendering equation can be approximated by equation 3. The font rendering process is summarized in algorithm 1, which can be found in appendix. We have visualized the rendering process in Figure 5. As shown in this figure, the generated font image gradually transforms from the source style to the target style, where the unrelated font pixels in source images are dissipated, and other pixels of target font are gradually created. Moreover, for the creation process, the skeleton of the font is first generated, then the fine-grained details are added, and the structures of the character become smooth and complete. Finally, the overall network is shown in Figure 6. Our font generation method contains 4 parts, including a style estimator, a structure encoder, a neural transformation field, NTF, and a discriminator. We use the following steps to generate the font images. With the reference images and a source image, the style estimator estimates the locations from the reference images, and the structure encoder network embeds the structure information from the source character. Then we generate n sampling points from the estimated path and combine each sampled location with the structure embeddings as the inputs for NTF. Since the current results are not dependent on the outputs of previous steps in the NTF function, we can parallelly calculate NTF function with respect to the different locations. Finally, we collect the predicted creation intensity and dissipation rate at all sample locations and utilize font rendering formula to generate font images. We conduct several extensive experiments to demonstrate the effectiveness of our proposed model. Figure 7 provides the qualitative comparison between our NTF and other state-of-the-art models. Our NTF generates high-quality font images than other state-of-the-art methods, which have better structure completeness and style consistency. Table 1 provides the quantitative comparison between our NTF and other state-of-the-art models. In few-shot font generation settings, we can find that our model achieves best performance in terms of SSIM, LPIPS, and FID. Table 2 presents the inference running time, number of parameters, and computation complexity of our model. It's worthy to mention that, in our model, as the sampling points increase, the number of parameters remain constant, while inference running time and computation complexity will increase. All experiment results demonstrate the effectiveness of our NTF, and we hope our current work can provide some novel insight on font generation task. In the end of this presentation, we summarize the contributions and limitations of our current work. In this paper, we regard font generation as a continuous transformation process by the creation and dissipation of font pixels along the transformation path and embed such transformations into the neural transformation field, NTF. This provides new solutions and insight for font generation task. Moreover, we develop a differentiable font rendering procedure to generate font images. Furthermore, the experimental results demonstrate the effectiveness of our proposed method. Our method mainly has two weaknesses. Firstly, the computation complexity will increase, and the inference running time will decrease when we utilize more sampling numbers to perform font rendering. Secondly, since only few reference samples are provided and does not cover all strokes, some local details of generated images are imperfect. Therefore, the few-shot font generation task is still a difficult task and need researchers to develop more powerful models. We hope our current work can provide some novel insight on font generation task. This is my presentation about our paper, Neural Transformation Fields for Arbitrary-Styled Font Generation. Thanks for your listening.